Okay, so how will our file encryptor work? Well, we're gonna create an out file which consists of the first 2 bytes is a random number between 1 and 65,536. Then we will have some padding. So if we have the random number 500, then 500 bytes of random bytes will follow. Then we have a 256-bit hash value, which will be our hashed password or hashed encryption key. That's so we have an ability to check if we have supplied the correct password or not. And then after that, all the contents of the file. And all of this will also be encrypted using the same key as is hidden in the SHA hash. And if you want to know how this works and why I need to do all of this, and I have recorded a special episode just for that, which I will also link to in the description. Okay, so let's start coding. As usual, I'm gonna start by defining the main, so I know what functions I need and when to do them, etc. And then I will start filling out those empty shells with real functions. I call it a function signature driven software design. Okay, so let's include stdio and all the other ones that let's put that in the H, by the way. So we'll simply include fse.h, and inside of here I will put all my regular include files. Perhaps we won't be needing all of them, and then we can remove them later on. But this way we don't need to pause all the time by looking at and finding these include files. String.h, and finally we also need our very own arcfour.h. And let's create a signature for our main int and char double star, like so. So how do we want to structure this? Well, we're obviously gonna need an arcfour instance and we are gonna need a key, an in file, and an out file. So char, or let's use our own integers. So int 8, let's make it easy. We can convert to our own when we need it. So char, and what did I need? In file and out file, and we're also gonna need an in fd and an out fd. So that's a file descriptor that we get from the open syscall. and we're gonna need an int 8 for our key. And then we need a couple of sizes. At least we need the size of the key. So let's do an int 16 key size. Like that. Okay, so if argc is less than, how many do we need? 1, 2 is less than 3. Then we're gonna print to standard error and tell that the usage of our binary file is in file out file. And the first is argv, and that's all. There we go. I hope the text size isn't too small for you. And then we're simply gonna return -1. And now that we have enough arguments, we can assign our in file to argv1 and our out file to argv2. A little bit easier to handle, so we don't have to remember which these are. Next step is asking for the key. Well, let's open the file in file first, because we want to abort early if we're not able to do that. So in fd equals open, and we're going to supply the in file, and we're going to do read only, like this. And if in file is less than 1, printf std unable to open. No, let's not. Let's just do print error open and return -1. Okay, so now the in file is open. Let's do the same with the out file, by the way. So out fd equals open, because the file may already exist with the wrong permissions or be badly formatted, etc. So let's open both. Out file, and this is write only, and we also need create. So we create the file if it's not there already, And we also need permissions for the file, and that'll be 00600. So only our user will be able to read and write that file. And if this open operation fails, then fd will be the less than 1. And in that case, we want to close our inFD, and then we'll do the same as before. Like this. Okay, so now both our files are open. Let's read the key. So key, let's see. We need to have a function which reads both the key and the size of the key, right? But since we are reading the input from the keyboard, we can just do a string length on it. We need to improve this when we do our much more secure version in the future sometime. Okay, so key equals read key, and maybe we'll supply some kind of a prompt. Key, like so. And in this case, I will do an assert. So we also need to include all the assert stuff. And that is basically two things we need to include. Assert.age, and we need to define GNU source. If we don't define the GNU source, the assert function will still work, but another function, which is assert p_error, will not. But if we have that definition at the top of our H file, everything will work perfectly fine. Okay, let's see. Int 16, no, it should be an int 8 pointer, which we called read key, and int 8 here as well. So we need to basically read the key from the keyboard, and don't echo the characters to the screen. So let's see. We'll wait a little bit with that. We're gonna set our, what did we call the key? Key size. Key size will be equal to the int 16 of string length key. Now let's do char like so, and then we can change our key to int 8. Okay, so we have read the key. Next step is to start reading from the standard, no, the next thing is to start writing to the file. And the first thing is those 2 bytes of padding length, which will be completely random using a secure rand function. So we need that secure rand function. So let us let's create an int 8. Let's see. We need to have, let's do int 16 and we will call it the padding length, pad size. And the actual padding will be stored inside of that int 16, right? Yes. And we need an int 8 array for the actual padding bytes. Like so. So basically we will do something like pad size or pad size equals secure round, and we need 2 bytes, something like that. Pad size I'm not sure if that's the best way though. It's a little tricky to store these kinds of data. Well, how do we store it? Because we're gonna need it for an int 16 like this, but also for a long string of characters. I think we'll do 2 different variables. That must be the easiest way. So let's say we have an int 16 called pad size 16, and we also have an int 8, which is the pad size 8. That should be it. So pad size 8 will be equal to this, and pad size 16 will be equal to let's see, we need pad size 8 dereferenced. So let's have it's a lot of variables for the same thing. This can probably be done much better, but I don't care right now. I just need something that works. So pad size 16 equals the int 16 version of pad size 8, and the actual pad size will be pad size 16 dereferenced. That should be it, right? I think we need to print this out to see if it really works. Pad size %d, and this will be the int of pad size. This is a lot of different conversions. Well, let's see if that works. Right. Okay, so the only thing is we have the opening of files. This is commented out, and then we have this. So then we can start with this secure RAN thing. Yeah, let's do that. Close infd, close alt fd, free pad size 8, return 0, like so. Okay, so how do we create a cryptographically secure function for generating random numbers? There is actually a system call which is called if we go into the urandom, I think there should be get random, and that is a system call. So basically it returns the size of a buffer of a specific size. So if we say that we need 8 bytes of random data, we get that, perhaps, or we get less. That depends on the entropy pool. So basically this function uses a lot of different signals, like what has occurred since the computer booted up, all of different things. It puts in a big pool, which is called the entropy pool. So you can only create a finite amount of these random bytes between all the whole system. And when you run out of entropy, you just have to wait. So you can call this function with 2 different flags. First, we're going to call it with give us all that you have, and exit if you don't have enough. And if we don't get all the bytes, then we will call it again, but we will put a message to the user that this may take longer than usual. And then we'll call it with other flag. Well, the alternative is that we don't use a cryptographically secure version of this, and I want it to be unhackable. So this is the stuff. We're gonna use this random which means that it doesn't use a pseudo-random function, which is not good enough for cryptography. So we need to supply the random, and then it relies on the entropy pool. And basically we will let it be non-block the first time around, and the second time without the non-block. Easy as pie. So size, return value, and we have the buff and the size. And I think we can supply a null buffer to get it on the heap. Or perhaps not. Never mind, let's allocate that ourselves. And where is this? sysrandom.h. So let's go into our h file and include sysrandom.h. And let's see, this will return an int8 array, and we called it secure rand, and we just need to send number of bytes. Let's do int16. And let's create this function. So int8 array and secure rand. We will have an int16 size. And we need to have an int8 pointer. Let's start by checking the size length. So we need to assert that size is bigger than 0, and yeah, that's basically it. P will be equal to an int8 malloc of size bytes. We will assert P, or by the way, let's not assert P. If yeah, let's assert P. If we run out of memory, so malloc will start to fail, everything will fail anyway. So okay, so now we have our buffer. We need something that catches the return value. Size T and will be equal to get random, and it will be P. Perhaps we need to, no, we probably don't need to typecast that. and then the number of bytes, that size. Maybe we need to typecast this to a size t. And we need the flags. Right. So this, and then we have the same but non-block. So we need it to be random, and we need to be non-block. So this may return, let's do if n equals size, then everything is okay, and we can return p. And if n is less than 0, something has gone wrong, and we need to return 0. Else, it means that we did not get enough bytes, which means we will have to run this again. So we do f printf stdr warning entropy pool is empty. This may take longer than usual. Something like that. And then we call it again, n equals get random. And this time we need to increase the pointer p plus equals n. So we will supply p, and this time this value will be size minus the n bytes that we have already gotten, right? And we need to supply the grnd random, but not non-block. There we go. And if n equals size, we return, we need to deallocate, by the way. And right. Yeah. Then we need to save a copy. We can't free it if we have jumped it around. Well, we can just jump it back. That's better, actually. No, we don't know how many bytes. Okay, let's do it this way. no hesitation. So if n equals size, then we return start. If n is less than 0, then we will free start and return 0. And in all other cases, it has failed again. So we can simply do else here instead. And this should be our function. So if we call it with 2 bytes, like this, and everything is okay, we should get different result each time. Let's see if this even compiles. Nope. But when does it ever first time? Int main. Second argument of main should be char star star. What did I do? Ah, forgot 1 star. We can't make the main a single star. There we go. 1 gone, a couple more to go, right? Open. Did you mean p open? No, I did not mean p open. That's a library called for noobs. Let's see. Open, what do we need? Man2 open, what do we need? Okay. So let's include this FC and TL whatever. If in file is less than 1, comparison between pointer and integer in file. Where is it? If in file, if in FD, alt FD, this one was right. In date padding, unused variable. Key size set but not used. Warning, unused variable. But it compiled. So let's see what happens. FSE. Yeah, we need to mock these files. Let's just touch in file. And let's do FSE in file, out file. 45938, 40950. Yeah, this works perfectly well. Great. Okay guys, let's create the read key function, which will be a quite simple function. It's going to read the key from the keyboard, and The only thing we have to make sure is that we don't echo the characters to the screen. So the only thing we're gonna have right here is a prompt, and what do we need? We need a buffer represented by a pointer. So let's see, we're gonna return an int 8, so let's make this an int 8 pointer. And we're gonna, let's see, we need a temporary buffer on the stack because we don't really know how many characters to allocate. So let's say, let's do unsigned char. No. Let's do char, and let's say we have a max limit of 2048 bytes. Or that's a bit much perhaps, because the biggest size in a 2048-bit encryption system is 256. Okay. So let's make it 255. No, 256. Because as you know, this isn't the index. This is a number of chars that we want to allocate. So counting the 0, it's 256. Okay, so let's begin by writing the naive version of it that echoes to the screen. And then we will simply fix that afterwards. So how do we do with this? We don't have to make it so difficult. Let's just begin mem setting. I shouldn't call this argv buff. We're gonna mem set the buffer with 0, 256 of those. Then we are going to read from standard in, standard out, standard out. From standard input into our buffer, and we have to, no, we don't have to cast that. And we're going to read a maximum of 255. So we have room for the ending 0 as well. Okay, so now we have read one line. We need to remove the ending new line from the input as well. And we're gonna need an int for our, let's do an int 32 for our length. Oh no, why should we just be as big as that? An int 8 should cut it, right? So size, and we'll simply just call string length on the input. Buff, and then we will, let's see, if we have A, B, C, D, That's the length of 4. And the indices will be 0, 1, 2, 3. And if we have a new line at the end, this will be index 4, and the size will be 5. So let's do an index as well. And index will be the size -1. So let's do let's point our pointer towards buff plus index, and let's zero that out like so. And then we will allocate our buffer. So this will be an int malloc size. And if malloc fails, everything will fail. And if it works, we will simply copy our string to p from buff, and the size will be size, right? Or maybe -1, by the way, just to make room for everything. Okay, let's remove this. And did I forget anything? Yes, we need to typecast a little bit. So the size is an int 8. So we need to make this an int 8. No, wait, an int 8 like this. And we need to send we can send the buffer as is. Read buff, memset buff. Int 8 malloc. I'm gonna string copy to p from buff. I think this will work, right? Perhaps we need to cast this one. And then we'll simply return p. We also want to print our prompt. Let's not forget about that. So let's do printf, and then our prompt and the space. And we'll give the prompt right here. And then we need to flush the buffer because we are not ending the printf line with the new line. So we need to flush it manually. Standard out, like so. And here is our first version of that code. Did we create our yes, but we didn't make this an int 8. This should be a char. Okay. So let's try it out without the echo, with the echo. Where are we? Key equals read key, third key. Yeah, let's try it. So make, okay, what is it? Differ in signedness. P equals buff plus index. So it's this line. So P equals buff, which is a char. So we need to do int 8 star plus index. Don't think that will be a problem. And P equals, let's try it out. Okay, we got a binary. Yeah. Okay, so let's try it out. In file, out file, key ABCD. We still have that pad size thing. We can remove that, but it seems to work. Okay, guys, let's end there for today, and we will continue this project another day. Don't forget to like and subscribe, and thanks for watching, and thanks for today. Let's remove that. So printf pad size. Yeah, let's just delete that. Okay. Okay, guys. So now that we have our key retrieval function, we will need to improve it a little bit and remove the echo of the keyboard characters from the screen. So in order to do that, we need to use a function and that is located in a header file which is called termios .h, and let me see if there are any examples. Let's see. Okay, so there doesn't seem to be any examples, but what we need to do is first, because they're in a terminal, there are a couple of options that defines how the terminal should work. So we need to do two function calls. We need to retrieve the current options of your terminal. Then we need to alter one of the flags to remove the echo. And then we will do another call to change the flags. So that's how we toggle the echo. And then we will just call our own function twice. Once for removing the echo and once for getting the echo back. So let's see. Let's begin by importing that H file. It is called termios.h. We also need to create a function. Let it be a void function that we can call toggle echo. And we don't really need any parameters, like so. So if the echo is enabled, we remove it, and if it is disabled, we put it back. Perhaps we should, yeah, this will be easier. Let's do a change echo instead, and then we'll take a bool, which will say if the echo should be enabled or disabled. So we need to include the stdbool.h as well, like so. So let's write the function, and it will be a void function that we'll call change echo, and we'll have a bool enabled, like this. Okay, so the next step is we need to create a structure, an instance of a structure for this kind of stuff. And let me see which one it is. We're going to use these two functions, which means we need a struct termios. So let's see. And I closed the window. Let's go into our directory. It is called FSE, right? No, it's inside temp FSE. There we go. Okay, so first I need to reset the home directory. Like that. And we need a struct termios t, and let's allocate some memory for it. T equals struct termios malloc, size of struct termios, like so. Let's copy both of these function signatures to make it a little bit easier to use them. So first we call this get attribute. So tc get attribute, and the FD follows the same logic as standard in, standard out, standard error. So this should be 0. Get attribute, and then we have the T, and that's basically it. Perhaps we need to send a reference to the T. Let's see if it works or not. And let's see what flag we need to alter. I think it's called echo. There's a couple of them. I think we just do the echo. Okay, so we need to do a binary operation. So basically T is equal to, no, T dereferenced is equal to, let's see, we need to remove a flag, so we will do a logical AND operation. And that might seem a little bit non-intuitive, but basically if we have X and Y and we let one of them be 0, then this will be 0 as well. If we use the OR, it would still be 1. So we remove echo, and now we need to do an if first. So if enabled, then we're gonna add the flag. No, if it is enabled, we're gonna remove it like we did. And if it is disabled, we want to enable it. Or what is most intuitive? Perhaps we should treat this enabled as if it should be enabled or not. So if it should be enabled, then we should do the OR operation and remove the echo. Else we do the AND operation. And then we basically do the other one, tc set attribute, and we give the file descriptor int optional actions. I think we can do the 0 there. And then we need to give the structure. Let's see, construct terminals, yeah. And that's it. So let's see if this works. In our, not this one, in our read key, we will send the prompt, then we're gonna do change echo, and we want to remove the echo. And then we will do it again, change echo, and this time we want it to be enable. Oh, so true. It should be false up there, right? Okay, let's see what happens. Make, okay. Invalid operands to binary or, yes, of course. We don't do it on the whole structure. We need to do it on one of the fields inside that structure. So let's see which it is. Input modes, output modes, control modes. So should either be could actually be any one of these. Let's see, if we search for echo and we go upwards to the headline, C flag constants. Okay, so the same flags are for all of these. Or what did it say? C flag. Okay, let's try it on the C flag. It's tough to remember all of these different functions that you only use once every couple of years. Let's see, where were we? Here. So this looks right, but we're gonna do T C flag and T C flag, like so. Not TC flag, it should be C flag only. So, right, C flag. It's a pointer. We need the arrow, not the dot. Let's try it again. TC undeclared. TC flag. Okay, now what? Invalid type argument of unary star have TC flag F, aka unsigned int. Well, we should probably not dereference that one. Where are we? Let's do it like this. Okay, so now we only have one error left. Has no member named C flag. It's tough to get this right, huh? It should be C flag, right? Let's double check this time. C I flag, CC flag. Let's copy this instead. So remove the whole thing, paste this in, remove the whole thing, paste this in. This time I'm feeling lucky. Okay, let's try it out. So we have in file, we have out file. Okay, it didn't really work. Why didn't it work? Perhaps it's because of this 0. Or maybe they want us to do this on the standard out. Because logically it could really be either one, right? So make, let me try it again. Nope. Let's do an S trace. It runs the command. So let's see the first time. Where is the first time? Here we get the flags and it has the echo. Then we set the flags. And do we have the echo? No. Well, yes, it's still there. Why is that? Let's see. So, oh, I forgot to free that one as well. But that's not the cause of the error. Let's see. So we get the flags if enabled, and it should be false the first time. Read key, change echo false, yes. So TC, oh, I mixed them, didn't I? If it should be enabled, we OR. If it should be disabled, we AND. Okay, so let's put this way instead. And let's go back to the 0. Let's try it again. In file, out file. No. Let's try it on standard out then. So 1, 1. Perhaps we shouldn't do it on the C flag. The other one, what did it say? One has to do with input and one has to do with output. Input modes, output modes. Is this an input mode or an output mode? an echo. Well, it's both. Well, let's try it with an I input mode on the standard input. So I flag and I flag. If it should be enabled, we add. No, we had this right the first time. And we want to do it on the standard input. The standard input. Okay, something happened. I can't press enter anymore. That's pretty weird. So we did change it somehow, but not really the way I intended. So let's just try one thing. If we do one here and we do it on the I flag, same thing. So let's do the I flag on the 0. No. Okay, so get attributes, file now, standard input. Okay, so now I looked it up. We should do it on the standard input as we thought, but we should do it on the L flag. So let's try it again. In file, out file. Okay, that's a bit weird. No, that's not right either. Okay, guys, let's end there for today, and we will continue this project another day. Don't forget to like and subscribe, and thanks for watching, and thanks for today. Sup guys, welcome to today's show. Today we are going to start a new project, and I will code something called FSE. And I'm gonna wait a little bit by telling you all what that stands for, because that would ruin the surprise for next week's project. But we are going to focus on the ending E in FSE today, and this is a file encryptor. So we have two different files. We have FSE, which will encrypt a file. You just give it a from and a to. And then we have FSD, which will do the reverse. It will decrypt the file. It will ask the user for the key, and here is the thing which makes this project interesting. At least I think so. The program will be able to say wrong key. If you type the wrong key, the program will be able to detect that, and if you type in the right key, the file will be decrypted accordingly. So why is this interesting? That's kinda self-explanatory, isn't it not? Well, it's not very easy to do, because if we're using the encryption that we did a couple of lectures ago, when we wrote a project called arcfour. If you missed that episode, that was an episode about an encryption library, which uses the arcfour stream cipher. And it doesn't matter if you haven't seen that episode yet, you will still be able to code today, but you will need to link that the library when you compile. So let's say we have a program that looks pretty much like this. We give two arguments, two files, and we supply a key which is not being echoed to the terminal, and we just use the arcfour to decrypt the file. Then it will not fail if the key is incorrect. The only thing is it will produce the wrong output. So the output file will be a lot of random garbage, basically. And if you provide the correct key, it will be the right file. And that makes it very difficult for checking if the key is correct, because the program does not know what kind of a file this should be. It could be a regular ASCII text file, like in this case, but it could also be any type of binary data, like a MySQL database file or anything really. So it's impossible for the program to use the output file to see if it has worked. You could do some form of analysis and have some kind of fingerprint database for different file types, I think there is something with relate to MIME you could use, or there is also a Linux command which is, I think it's just, you type file and the name of the file. I think that is it. But that is not 100%. It doesn't know every format out there. And even if it correctly identifies the format, there is nothing that says it can't be two different files with two different keys with different contents of the file but the same format. So that is doomed to fail. The only way to be able to do this will be to include the key somehow in the input file. Okay? But there are a lot of pitfalls when you try to do something like this. Because if you make one wrong move, you will either make the encryption very easy to crack, or it will be worthless. Okay, so how can we go about this? Well, one way would be to, let's say this is the file contents, the clear text file contents, and let's the thing on the right be the ciphertext. So CLCI, and this is not even relevant for us right now, because the decryption tool will only be dealing with the ciphertext file. So let's focus on this one instead. So what can we do? Well, we can take the encryption key and put it in the beginning of this file in the clear text. So let's say if the key is tomatoes, then we put the regular ASCII string tomatoes at the beginning of the file. And then we either have some kind of separator. Let's say we have a double pipe sign, and then the actual file contents start. That's one way. But we are talking about the ciphertext. This is an encrypted file. So if we have the key in clear text inside of there, it would be a problem, obviously. We could, however, still keep the key right there, but we encrypt it. So basically we just add the key in clear text to the source file at the beginning, and then we encrypt this, and then we continue on encrypting the rest. And of course this is more secure than the first option, and this might be kind of tricky to crack, but we will most definitely open it up for making the security less than if we didn't have the key right there. And we don't want it. The task is to make this possible, but without in any way making the encryption less safe and easier to crack. So, and why is this
decreasing the security? Well, when you try to crack something, an encryption, you want to have small pieces of information. Well, actually, you want a big part of information if you can get it, but basically cracking depends on you looking for weaknesses, looking for patterns in the algorithm, in the output, in the way the key is generated, in the way you do random bytes, etc., etc. And if the coder does something wrong, it gives the cracker information, and every 0 or every 1 of information that they obtain will make it easier to crack. It will lower the possibilities, because a cracker usually it makes a computer test every possibility according to some scheme. And if you have parts of information, then you don't need to crack every combination. You can leave something out. And this can also lead to more information because of other small bugs, etc., etc. So if the cracker knows that the beginning of the file, and we know how big the encryption key is, it's somewhere between 1 to at most 2048 bits. So in the first 2048 bits, we know that the key will be stored, encrypted in the same way as the rest of the file. And this is a lot of information, and it's a very, very important information. So this will most definitely lower the lower the security of the encryption suite. Okay, so this is not a valid way to do things. Let me just clean this up a little bit. Okay, so what else can we do? Well, we can take this. Usually you don't store passwords in clear text, not even in an encrypted file. What do you do with them? Yes, you create a hash. A hash is a one-way encryption between quotes, because it's not really encryption. It's hashing, but you can describe it in one sense as a one-way encryption. So if we take our key, for example, we can turn it into a string of bits. And no matter if you obtain this string of bits, you cannot go in the opposite direction and reobtain the key. The only thing you can do is, if you try out a password, for example, then you can encrypt it the same way, and then you can look at both results and see if it's the same hash. That's the only way that you can use a hash. So let's do that. Let's select a hashing protocol. it will probably be some of the SHA hashing algorithms. There is SHA1, and there's I think 128 is one of the more secure. I need to check up on that. But one of these SHA ciphers, and I don't know exactly, but this probably means that it's 128. But anyway, let's say the first 128 bits of the file will be that encrypted hash. Well, that makes it better because the SHA hashing algorithm is most definitely stronger than what we had before with just arcfour. Okay, but this is still not good because of the same reason as the last time. If we do this, then the crackers will have absolute knowledge of the first 128 bits of the encrypted file, even though it's hashed, and they won't be able to use that per se in order to turn it into an encryption key, but they may still use informational parts of it in order to crack the cipher in other ways. So we don't want to do this, but we still want to use the hashing algorithm, SHA. But where do we store the hash? What if we put it on line 5 or something, a couple of characters in? Well, we still would have the same problem because it's an open implementation. The crackers will still know where this will be found. So we need to store it somewhere in this file, but different places every time. How can we do that? And how can we find it the next time? My idea is when we encrypt a file, the first thing we do is we produce a random value. Let's take a new page. So first we do a random value of 16 bits. That will mean a number from 0 to 65,535. And I will not use the 0, so this will be 1 to 65,536, I think. I haven't decided that, by the way. Let's do 0 for now. Okay, and where are we going to put that number? Well, first of all, we're going to put that random number, let's call that the offset number. Yes, this is the offset. So the first 16 bits will be an offset. But now you might go, wait a minute, isn't this the exact same problem like we had before? That the crackers will know exactly what this part of the file will be. Well, will they now? First of all, this is a cryptographically secure random value, which means it can be anything between 0 and 65,535, which makes it 100% impossible to do anything with, because you cannot turn it into something else, you cannot reverse engineer it in any way. So this should be secure. And what do we need this number for? Well, let's say we randomized the number 650. The next step will be to produce 650 encrypted random bytes. So the same cryptographically secure way that we created this random value, we will create a padding. And that will be somewhere from 1 to 65,535 bytes this time. Of random data. Which means that this offset will be exactly as secure as this offset thingy. Let me color this in. So the offset will be this yellow part, and then we will have our padding. Like so. That's the padding. Okay, and what comes next? You guessed it. The hash. And let's color the hash green. This is a little bit smaller. Maybe like so. And the rest, let's make that this color. This will be the actual data. And in this example, this looks like the data part is very small in comparison with the other, and it might be if it's a very small file, but more probable is that the next like couple of pages will be the data. So the data can be like several gigabytes. It can be any length, and then we will encrypt everything. So let's do something like this. So even the random data will be encrypted as well, and then written to the file. When we go the other direction, when we want to decrypt this file, well, then the program will ask us for the key. When we input the key, we will initialize our encryption engine with that key, and we will begin by decrypting the first 2 bytes of the file. containing the offset. And now there's two possibilities. Either we have the correct key and we get the correct offset value, or we have the wrong key and we get any random number between 0 and 65,535. Oh, and let's say we did get it wrong, the wrong encryption key, and this number is, let's say, 30,000 or something. What we'll do is we will skip the next 30,000 bytes, but as we pass through it, we will decrypt this data as well. And that is so the internal state of the encryption engine will be correctly correct when we will start decrypting the real data. And then we are at place 30,000, where we believe that the hash is located. We can't really see if there's really a hash there, because the hash won't be in any ASCII format. It will be in a binary format, taking up like 128 bits in this case. So we will read that data, we will read the wrong hash and compare that to our wrong password, which will not work. And then we can say wrong key. For it, in order to, and then the program terminates. For it to really work, we will have to do this again with a real password, the real key. So let's say we have the real key this time. We will decrypt the first 2 bytes and we will get the correct offset of 650. We will jump past these 650 bytes, but we will decrypt them one by one as we pass them by. Then we will take the next 128 bits, which we think is the hash, but maybe not. Then we will encrypt our key with, we will hash our key, and we will get a hash back. And this hash we will compare to this hash. And this time we will succeed. So we can tell the user correct key decrypting. And then we will decrypt the rest of the file 1 byte at a time, all the way through, and we will write only this blue part to the file, discarding the offset, the padding, the hash, and only writing this blue, which will be clear text data. So this is my idea, and I think it's gonna work, that it's gonna be a secure way of using the arcfour cipher. One prerequisite is that we use the whitewashed feature from the library that I showed you last week. But those two in combinations, this way of handling the files and the hashes and the keys, etc., in combination with a secure way of creating keys, that would be the third. But most important, we will have this way of expressing if we have the right key or not, and we will have the whitewashing feature to don't be affected by most of the recent bugs, etc., which has been found in the arcfour cipher. So I believe that this is the solution to creating this ability to say wrong key if it's a wrong key without in any way decreasing the security of the encryption engine.
I know, Abby, a lot of people have been telling me that I should create a Discord. I did create my own chat system. I don't know if you ever visited, and it worked pretty well, but I don't know. I don't really like those new systems which look like Discord, and they call it creating your own Discord server, but you're not creating any server, you're just creating a basic account on their server. They have all the power, they have all the I don't know, if I feel unwary not having the full control over my server, you know. Yeah, maybe Telegram, actually. It would be a greater fit, I think. But I would have to learn these new systems first. But I can promise you this, at least. There will be some kind of a chat in some form or another. And I hope you all will join me there as my regulars. Alright, so let's see. As usual, I will begin by connecting to my Linux server, and that is Code Planet. So let's see, I will do like this, I think. And I will connect to my screen. And then I'll go to the directory. I've prepared a copy of the last code in a directory which I called, what did I call it? FSC2. Yeah, FSC2. The first one was FSC. That stands for File System Encrypt or something. But it's not a file system, so... No, file send encrypt, because I was planning to add something which sends this stuff over the network as well. Alright, and I will set this to my home directory, as I usually do, because it makes stuff a little bit easier. And I will also create an additional screen in the same directory. And I intend to upload this to my repo. I don't know if you have seen it. If you go to https repo drbirch.com, you will get into this page, and not everything is available for non-members, but some is, and the code of today I will make public here a couple of hours after this live stream. So repo.drbirch.com, and you will be able to download everything from today, including any libraries that we are using. Alright, so I will set this to my home, like so, and then I will connect using the Sociopath SCP client. You have probably seen this in almost every video that I use. I use this in order to code remotely in VS Code. So I just select my directory here and choose open in editor, and it will download the stuff and monitor that directory on my hard drive. So when I save, it will automatically sync that. So let's see if I can fit this stuff inside of this HD 1080 window or whatever. Let's see, like so, and I will create a new file here, which I'll call fsd.c, and I will make this a little bit smaller. I hope you still are able to see this and it's not too small for you if you're watching from an iPad or something. If it is, tell me and I will make it bigger. Alright, so this is fsd.c, and I will just have this header for now, and I save, and hopefully, if everything works out the way I hope, I will just yeah, here it is. I will be able to see the file here. So every time I save or create a new file or create a new directory, etc., it will automatically sync that towards my Linux server, so I can use VS Code locally with ease. And if you want to find this program, I can show you that as well. Just a small parenthesis. You go to Google and you search for Sociopath SCP client, and you grab the first one here, and it says the graphical SCP client for Mac, but there is a Windows version as well. Linux, unfortunately not yet, but I will try to compile this for Linux when I have the time. I have a long to-do list at the moment. Alright, so now we are ready to begin the actual coding. Let me just take 1 minute and check the chat to see if there is something I need to take care of. Alright, let's just continue then. Okay, so how do we code this stuff? The encryptor files looks like this. So in the beginning there is a 16-bit encrypted number, and this number decides how much of the upcoming bytes to skip. So if this is, let's say this number is 5, and then I have a lot of random data here. What we are going to do is we're going to skip the first 1, 2, 3, 4, 5. So we can just delete that, poof. And then we're going to decrypt this stuff. One thing I forgot. We are going to decrypt this stuff, but when we decrypt the first thing here, it is the password in hashed format. So basically we decrypt this and we get some kind of a hash, and then we use this to verify that we have the correct password. It's a little bit hard to show just like this, but I will show you when we get to that part of the code. I'm sure you will understand then. Alright, so let's see, how do we do this? Let's create an age file. It makes life easier. So we do fsd.h, and as usual I put in some kind of a header here, fsd.h, and I want to include a whole bunch of stuff. So we start with the standard IO. I do also want the standard library, and I will want the uni.std.h. I might need some string handling, so I will use string.h. And what else? I need the assert. The assert is a function which checks a specific condition, and if it's false, it will exit the program. So it makes programs like this that I code on camera a little bit easier to write without a lot of error handling and stuff. But usually in production you wouldn't use this. And when I use this, I do also want to include some other stuff like rnumber.h, which makes for some additional functions. And in order for those to be working correctly, we need to include the new source up here. It's basically one function which is called assert p-error. In order to get this function, you need the assert, you need the error number, but you also need this definition. Let's see, there is a question, 2 questions actually. Anyone please tell me which one is the predecessor video of this decryption topic? Alright, can any one of you help shove out with it that it should be a video which is called creating a file encryptor. I think it's like that. And the second question, do you have a community on Discord? We were discussing this just a couple of minutes ago. No, I did have a chat, a chat server, which I created myself, but it didn't work out too well. I did a little bit of bad, what should I call it, marketing. So it never really left the ground, so to speak. Yes, we can have a video on RPC framework. Please remind me at the end of this live stream, and I will add it to my list. But no, we don't have a Discord community or Telegram, but we were discussing that perhaps we should create a Telegram community. I just need to learn that platform first. I only use it to read some blogs and stuff. I don't know how to use it myself. 52 minutes, that sounds about right. There is a sequel to it as well, which is called something like Keep Writing a File Encryptor or something. But the first video, 52, sounds right. Alright, so I will continue now. I have included the things that I usually use. I think I'm gonna do something like, I would also like to have the std bool.h so I can use booleans. I will not use the standard int though. I like defining those myself, so I will do that. So, for example, an unsigned char will be int 8. I will also define an unsigned int as int 32, and in between I want to do unsigned short int as int 16, and I do also want a type def unsigned long int, which is int 64, and the number is how many bits big or wide those integers are. So this is a basic standard int, and this is one which takes 0 to 255. This takes 0 to 65,535. The regular int goes to like 4.3 billion or something, and 64 bits is so big I have no clue. A lot of numbers. Alright, so let's include this file. Include, and I called it fsd.h, like so. Let's also create some function definitions. At the moment we do only have our main, and our main will take an int and a char double star, like usual. Right, and let's create an empty main for now. Like that. Return 0, just so we have something to try compiling with. And I do already have one of those. Let's see, make files. Okay, I don't see it here. Let's create one from scratch. I will just do it fast, so we don't waste all the time on creating make files. It's an art, you can work on it forever, but I would just want a simple one. So I will have flags, some optimization, and error messaging. I do also want to use the new C2X standard. Some LD flags. We want to use a library, which basically is, let's see, arcfour. That is my own RC4 implementation, an encryption library I wrote in C. There's a video about that as well. Alright, and as I mentioned before, I will make this public, and I will make this code public on my repo a couple of hours after this live stream, and it will be up for 48 hours. Alright, so let's see. Okay, so we begin with the fsd.o, which has the dependency of fsd.c. We compile this by running cc with the flags, and we are taking the input parameter with -c in front. When we have the O file, we can create the binary fsd, which depends on the O file. Let's make this depend on the fsd.h2, and then we need to change this to this, because this means the source, but if you have multiple sources it will mean both of them, and I don't want to use the H file when I compile. So then we can use this, which also means the source, but only the first one. Alright, so when we have the O file, we can compile the binary by running cc with our flags. Then we take the input and we do -o output, and this is the output variable, so this one, or the output file rather. And if we were able to zoom in a little bit on this @ sign, you would see that it looks pretty much like the thing you throw your darts onto, and that's why it's used for the target. Quite good memory rule. And we might also need some LD flags here. And to make our lives easier, we will also have a clean, which simply removes all the .o files as well as the FSD binary. We will have an all, which is just the we will run clean first and then run the FSD. And both of those are not producing anything on their own, so we will mark them as phony. And this ought to be the whole thing, I think. Minus any errors, perhaps. Let's see if it compiles. Did it upload? Yes, we have a make file. And if we run make... Right. I haven't configured on this computer. I maybe have not yeah, I think I should have done that. Let me see what it says. Makefile has changed, successfully updated to server. Maybe I picked the wrong file name. I'm trying to compile the old thing, perhaps. fsd.c, fsd.h, fsd.o. Why does it give me error messages on things I haven't even used? fse cat makefile. No, that's the old one. Maybe I haven't configured Sociopath on this computer to handle makefiles, because in the configuration, I can show you the configuration file. If we go to the Sociopath directory in your home, there is a config.json, and if you go to the end, you will see all the different files that it should monitor when you... Because let's say you have a big website and you want to open that directory in your editor. You don't want Sociopath to download all your images and video files and whatnot. You just wanted to download your code, right? So this is how it distinguishes for that. And usually I do something like add a line like makefile, so I can edit a makefile as well and get it uploaded. But I forgot to do this on this installation, and I don't want to restart my Sociopath now. So I will do some kind of a hack instead. Let's see if I can just rename this file to, let's say, makefile.c or something, and add something like this and save. And now it should have uploaded, I believe. Didn't I? Let's see what it says. It didn't react. Maybe it didn't save. Now it's saved. Now it reacted. Am I in the wrong directory or something? Temp FSD2. Where am I blind? Is it here? The funny thing is this program has always worked perfectly. Let's try it once more. That's very weird, actually. Make files. Oh wait, I'm. I created it in the wrong folder. That's why. It's, you see, it's outside of this directory, right? So we can probably rename this again. That was not the problem, I believe. And let's move this thing into there. Yes, move. And now you see it jump to the right. Right, so if we add a space and we save, this time it updated, it says, did it? Now we have a make file here, and it is our new one. Great. Okay, so it was a user error. Even if you have done this stuff for a long time, you still do mistakes like this. Okay, so let's run make clean, and let's run make, and it's compiled, and we have our binary. So now everything on that front is working according to plan. Alright, so let's see, how do we begin? What do we want to do? We want to, let's see, FSD, FSE, FSD, okay, that's right. And we want to have a program which takes one path at the command line, or perhaps two paths. Let's create a usage function to make it a little bit clearer. So this function will just print to the screen the usage. Maybe we should send the string as well, the argv, or just arg. So we will run the name of the program, followed by source file, or source file name perhaps, destination, or let's remove file name. I think that's pretty clear. So we go from source to destination. And let's add the arg here. So if we inside of the main have less than 3 arguments, because even the first one counts, the file name. And if we do, we will just do the usage. We send our argument. We need to send it as a char. And we return -1. Otherwise, we will have 2 variables. Let's call them source file, dest file. And as you can see, I use int8 pointers as strings. That's the same as char. Because I defined it here, right? Typedef unsigned char int8. Alright, so if we have those, we will just set source file to the int8 casted. That's right, this should be int8 as well. The int8 casted first argument, and same with the destination file, which will be the second. So now we have basically set up this stuff. Let's move down a little bit so I have space, and I will show you a little bit in pseudocode what we need to do, and then I will replace each of these lines one at a time when we are actually coding the functions. And that is a very good idea if you want to know or have tips how to structure your program. I get a lot of questions. How do I structure a real world application? And I think this is a good way. The first thing I always do is I define my different data types. It's not a lot of them today, but I do that. And I try to make them as expressive as possible. And then I do this pseudocode stuff. So first we want to initialize the crypto. And in order to do that, we need to read the password, or let's call it a key. We need to read the key from the keyboard, and we want to read it without echoing it to the screen. So that's one thing we have to account for. And then we will initialize the crypto, the encryption algorithm. When we have initialized that, we will decrypt, what should we call it? Decrypt int16. Because as I mentioned earlier, the first 16 bits of every encrypted file using this application, it will tell how many bytes to skip, because I want to save a encrypted or a hashed password inside of this file, so I can verify that you are using the correct password or key. And I want to hide that hash somewhere in the file, not at the same place every time. Because if I hide it, it will be very difficult to find it and try to break it if you don't have the key. So it adds security. So basically we will decrypt that and use that int16 to skip bytes. And this will be something like 1 to 65,535, something like that. And when we have skipped the bytes, we will read the hash, and we will also, so all this data is encrypted, right? So we will decrypt it as we go. Even the hash will be encrypted, and that's really unnecessary actually, but it makes it easier to code this program, and I don't see any drawbacks with it. Alright, so we read the hash, we verify the hash. So if this is the same as the key that we read, then we will carry on. If it's not, then we can display an error message. And then we'll simply decrypt rest of file and save everything from here on to disk, right? So this is just to verify that we have the right password. This is what should be saved onto the disk. This is the encrypted file. Okay, that's quite a lot of information in one go. Let me just ask you in the chat to see if you have understand what I said, and if you have any questions. So let's see. FJS, that is a good question. I mentioned it in passing in some other video, I think, that yes, they do provide these exact types, but they have one huge drawback. Anyone knows what it is? Anyone might have heard me say it before? Why do I not use the standard int.h? Any guesses? The correct answer is the name. The name is the drawback. It has an underscore in it, and I am allergic to underscores. I loathe underscores. There is nothing that slows down your typing more than trying to type that stupid character. So I never use any underscores. I never use any capital letters either, basically, because reaching shift while you're trying to type, no thank you. So at least not on a Swedish keyboard. So that's why I don't use standard int. I define them my own without those annoying underscores. Did you ever finish the encrypted executable video? Yes, I did. So there are two episodes about that. The first one's the 52-minute episode which is named something like creating your own file encryptor or something. And the second video is called keeping coding on a file encryptor, something like that. If anyone finds the sequel, please put it in the chat. If you are allowed to put links in the chat, I'm not sure actually, but try it out at least. Have you ever worked with OpenGL? No, I'm not really a graphics kind of guy. I like console stuff. C++ projects also. I get that a lot actually, but no, I don't know that language. I kind of skipped it. I know C and I know C#, but I never learned C++. So that will probably never happen actually. But all my C code, basically all my C code, will be compilable with a C++ compiler. So it's not really a problem, I think. And if it's not compilable, you probably just need to alter some minor thing or so. Simple engine. Alright, that's pretty impressive. Ben, that's good. We are the console guys. There is so much diff between C and C++. Yeah, it's quite a lot of rather bloated functionality in C++, but the basic structures are the same. You see C++ used in the industry. I'm not very good at career advice and similar things, but yeah, of course it's used in the industry. 90% of the code in the whole world is C, and the other 5% is probably C++. So yeah, it's used in the industry. Did you learn anything useful today? And do you want to support this channel? go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright, so let's continue our journey into the encryption world. Where were we? Right here. Okay, so this is what we need to implement. Those pseudocode kind of function. So let's begin. First, read the key. And I actually already wrote this function when I did the file encryptor. So I think I will just... I don't like copying code, not even my own code, but that was a rather boring function to write actually, so I think I will just do that in this case. So let's see, fsc.c, and you will get access to this code. Right, here it is. Change echo and secure run. No, that's not it. Read key. Here it is. So let's copy this thing. XP, and let's go inside of here and add it on the top somewhere, right here perhaps. So we need the read key, and there was one more function, right? This one. Let's remove this stuff and let's just copy this whole thing. I hope this code works. I'm not sure how far I got with this, but I remember I did finish the encryptor, right? So, because this is a project that I did a long time ago. It seems like eons, but it was probably like half year or so. Let's paste this here, and let's update our H file. So we added the usage. I don't think I put that here. Don't save. Let's see. So we have void usage, and it takes an int8 pointer, like so. And what else? We had some kind of... Let's just take this line. Yes. I'm talking to my cat a little bit here. He usually decides when I work or not, so because he jumps all over my keyboard when I don't give him the correct answer that he's looking for. Alright, so let's see. Void change echo, and this is a bool. I like that word, bool. And then we have the read key, like so. Let's just put it right here, like that. No, like that. And this is a char, actually. Why did I make it a char? I think I will change this to... Oh, no looks. Not right now, okay? Let's see. So, where was I? This should be an int8 pointer instead. I think I want that. And it gives an int8 pointer back, right? Alright, so let's remember to alter this thing. This should be an int8. And that makes... Oh, nej, looks. 1 second. Lux, nu får du lugna dig. Okej? Och så måste jag arbeta. Sorry. He is very determined sometimes. It jumps all over my things here. And I can't shut the door either, because then he's sitting outside and crying basically. So we need to change this to an int 8. And let's see. Memset of we read. We need to cast this one since we changed the types. And this one too. And it should be an int 8 here, and yeah. The rest is okay, I think. We need this though. What did I do now? Undo. This should be char as well. Alright, let's see. Okay, I did not copy the whole thing, but what will this return? It can't return a whole lot of different things. It must be P, right? Okay, so now we have functions for that. Let's make sure they work. Int 8, and this is some temporary thing just to check if this works. And we need to make a comment out of this thing. We can remove that. Alright. Anyone knows how many it's watching this live stream at the moment? I can't really check that, because when I tried doing that before, the sound started to loop through my web browser. So if anyone can check that and put it in the chat, I would be very glad. Alright, so temp will be equal to, what did I call it? Read key, right? Yeah, read key. And this will call change echo. So read key. Read key, and we give it some kind of a prompt, which needs to be int 8 casted. So let's say key. And then we will just print it to the screen afterwards to see that it works. Key is $s, and this is a char representation of TNP. And we return 0. So, okay, let's see if this works. So we make clean, move down a little bit, we run make. Oh, that's something. Invalid application of size of. Okay, so this function didn't really work as well as I was hoping. Where is that size of? This should be okay, I think. Which line was it? Size of 14 in fsd.c. 14. Maybe it's just because I haven't included the terminals. That's probably it. So let's see. We go inside of here and we include, I think it's called terminals.h. That's a library which handles like the terminals and stuff, so we can remove that echo when we type the password. Alright, let's see if that removes the first error. Oh, almost every error went away. Unused variable, and that's it. Okay, that's good. If we run this thing, and we just type whatever here, it asks for a password, ABC. Okay, it just reads one character, and it does not remove the echo. Let's see the chat, by the way. If you... Okay, 15. Missing struct definition. That was it. Good call. I am making a file decrypting software. 18 watching. Okay, it goes in the right direction then, I think. Alright, so this terminal stuff is really boring to get to work. It's like those annoying structures that you never really know how to fill them out. Let's see, we get everything to the T, and if enabled, let's see, if it is enabled, we OR the echo. Should be the other way around, right? Because we want to remove the echo if it's enabled, and we want to add the echo otherwise. Think so, right? Must be. But why did it react the way it did? It was just receiving one character. That's usually because we are messing up the rest of the structure somehow. Because there is one option. If we go to man terminals, I think, there is an option here somewhere which will... I'm not going to go through everything, but there is an option, believe me, and that will read one character at a time instead of a whole line at a time, which is the default. So that is probably what is happening, that I'm accidentally sending the wrong thing and overwriting that variable, or that part, that bit of the variable. Okay, so let's see what happens now. If we run this again, okay, same problem. Let's see, what am I doing here? First I run the tcget attribute, and I send a 0 and t. That should give me this structure back. Let's not make this a pointer. I don't really see why I should do that. We don't need to malloc this thing or free it. And let's send the reference of this stack variable instead. And let's do the same here. Maybe that's it. Maybe I sent the address instead of... But I don't think so. Okay, we need to change that because it's not a pointer. So this arrow, it's only for pointers. When we use regular variables, we just use a dot, like TypeScript or something. Alright, so let's run and let's try it out. Same problem. Okay, it wasn't that. I didn't think it was that, but now we at least have it a little bit better. So let's check out this function, tc get attribute, and it takes an fd, and it takes, okay, that's why I sent the 0, because the 0 is a standard file descriptor which is always open, and it's the keyboard basically. And then we send this reference to structure, and then we do the set operation. It's still an fd, it's still, no, it's an optional actions, and then it's the structure. And how did I do it? 0 0 t. I think that looks right. I actually coded this very same function a couple of weeks ago when I was coding on runlock, because I wrote this in assembly. Maybe we can check the assembly code and see what we are doing wrong. Where do we have this? I'm sure I uploaded it here somewhere. Maybe here, asm. No, it's not here. Do you see runlock pm mnopqr st? It's not in the temp directory, it's in the code, of course. So do we have it directly here? Runlock. Here's some files though, but directory runlock, here we go. Alright, so let's see, where did I put that? It must be inside of the utilities, but let's take the whole directory. So we do, and this is also a good thing with this tool. Even though I'm currently watching the other directory, I can add as many as I want. If you create additional processes of this, if you start this program like 3 times and you get 3 windows like this, then you can connect to 3 different servers, and you can code remotely on all 3 of them at the same time in the same VS Code window. Let's see, runlock, open in editor, and now it just downloads the code. I hope I did put .asm in my config file, but I think I did. And then I will just put it here and add it as workspace. And now I have access to the code. So let's minimize this SCP thing. And the interesting part is not here, because I don't show the ASM. I do show the ASM H though. Why is that? It's ending in H, that's probably why. Alright, but let's take the actual file then. Where was I? Here. Runlock and util.asm. And it says I don't know the ASM files, but I can choose an application, and it's called Visual Studio Code, right? Or is it just code? Code. So if I double click again, that's right. Okay. So here is part of the runlock code. I will make this stuff public when I am done writing this tool, but I'm halfway through or a little bit more. And this is basically a include include library or whatever, where I put a lot of different utility functions and stuff that I might be able to use in several projects. And here is the example of the Termios structure that I'm currently working with. So let's check out the function for that. Read one, read, exit, reset terminal. No, that's not it. I think I scrolled a little bit too fast. Here's get password. So what does it do? It runs echo off. And that's basically what we want to do. And echo off is a macro which is included inside of the H file. But I was able to reach the H file, right? That's right here. Right, so let's search this file for echo off. And what does it do? It runs another macro which is called secho, and it gives the argument through. Let's see. tc get s push. So this is my variable for the structure, so to say. And we call this ioctl command. Okay, I've made it a little bit more low level than in the C code. I'm not calling the terminals functions, I'm calling the system call in the kernel directly. Perhaps that is easier. Let's see, ex, exx, edx, ebx. And what do I do with this input if we want to set this? I will simply do an AND operation. That's right. Alright, so let's try to replicate this. First of all, we need that structure I showed you before. This one. And as you might imagine, we can't use that right on or whatever. I don't know how to say it. We need to modify it a little bit, right? Because it's a different syntax. So this is basically a variable. It's 20 bytes in size. And then we have, okay, this is not related to what we're doing now, I think. I think we are actually, I copied the wrong thing. Didn't I? Yeah, this is what we need. Lux, var snäll nu. Husse måste arbeta, du vet att jag vill det. Oh, we are actually on overtime. As I mentioned before, I intend to do a lot of these spontaneous live streams at different hours. And my goal is to have like an hour or something, depending on how much time I have at that specific moment. I will not end this right away, but it's about an hour. That's what I was planning, and I will always use this to continue on an old project like today. And I will make my new projects as regular videos, but I will publish the live stream recordings a couple of days after. Alright, so let's see. If we just paste this thing here, let's see if we can handle this. So all of these are, DD means it's a 32-bit integer. So that's pretty easy to handle. This will be an int32, int32. Alright, sorry, I think I need to have to take care of my cat now. He decides when I work and when I not work. But there will be a new stream very soon, and I will continue this program, this project. I will also publish this code in a couple of hours on the repo. You know the repo, you find it here, repo.drbirch.com. And it will be publicly available even for non-members for 48 hours. And hope you liked this episode. If you did, please like and subscribe. And thanks for watching. Thanks for today. Let's see. I'm gonna connect to Code Planet and I'm gonna attach my screen. And I think we used 250 the last time. Yeah, we were dealing with this terminal stuff. That's right. So let's see. I will start by going into the correct directory and see if I can find this one. I think it's FSE2. Yes. And I right click and I choose Open in Editor. And what this does is it will simply download all the files and subdirectories, and when we update anything locally, it will automatically sync that against server. So basically we are coding remotely against this server. So let's see if I can fit this window inside over here. So let's pull it out here, and that will be good, I think. Perhaps I should make the text a little bit smaller. I hope you're not having any trouble on small screens to watch that text. Alright, so let's see what we did last time. We were coding this decryptor tool. We created the H file with some pretty basic stuff, basically the same things that I pretty much always start with a project, and then basically the same here. What we did was we defined the different steps that we are going through in pseudocode. So first we want to read the key from the standard input, and we want to read it in a way that it doesn't echo to the screen. Then we want to initialize the encryption. We want to decrypt the first 16 bits of the file. And those 16 bits, it contains a number between 0 and 65,535. And that basically says if it's, let's say, 600, then it will skip the next 600 bytes. So it's a padding mechanism in order to make this hash a little bit harder to find. Because if we just put the hash in a fixed location, then anyone can find it and possibly crack it. But if we conceal the location, so it can be anywhere inside of over 60,000 bytes, that means that if they want to crack this hash, they need to crack 60,000 hashes, not one. So that's why. And one important thing is that this padding is truly random, and that the hash also looks like random bytes. So it should be indistinguishable from each other. Then we verify the hash against the key that we read from the standard in. If it's the right key, we will start decrypting. Otherwise, we will simply throw an error. And then we decrypt the rest of the file and save it to the out file. Pretty basic setup. Alright, so we were having a little bit of trouble with this disabling the echo step. What I did was I took this structure from my assembly code, because I wrote a similar function in assembly not long ago. So I thought perhaps we could use that. So let's turn this assembly structure into a regular C structure simply by renaming these commands to int32 and removing the dots. We should also remove the things to the right. And let's see, C. This is not, those two last is not in 32, they are in 8. So int 8. And now we can remove this stuff. And we also need to change this up a little bit so it matches the C syntax of a structure. So let's call this struct terminals. And let's do something like this. Alright, so now we have the actual struct. That's step 1, so to speak. The next thing is basically that we need to use the ioctl command in order to turn off this echo. So if we go to our terminal and we do, let me just check that this terminal is visible. I will move it a little bit and perhaps shrink it as well, something like, we don't have to see all. This is good, I think. Alright, so what we do is we do man ioctl terminal, or not terminal, maybe just term, or tty perhaps. Yes, here it is. Okay, so these are the, because this ioctl syscall is being used for a lot of different IO instructions. or operations. So we need to find the right one. And what we want to do is, let's see if there's an example, if we're lucky. Okay, win size. There's a lot of stuff in here. Alright, so maybe I can peek a little bit at my old code. I don't like copy pasting code, but since it's my own, I think it's, as an exception, I think it's pretty okay. So let's see, let's create a new window and let's go to code and file send, and let's see, so we go to the encryptor. There's all of these different amps. If you don't know what this is basically the Windows version of a new line. So that's what this editor that I'm using, VS Code, it always appends those, but they are quite annoying when dealing with Linux. So what you can do is you run the call command, and then you take an input and you output it to something, let's say ABC inside a temp. And now we should have gotten rid of those stuff. Good. Alright, so let's see. Here we have echo. I think this will do. So let's do this instead. So we can remove this one. It becomes too complicated in this case, I think. So let's see, we have a change echo function here, but let's use the one that I know works or at least I hope it works. So we have bool echo bool on. Let's go into the H file and update our signature. So this is just echo, right? Yeah, echo. And it's a bool and it takes a bool. Alright. And we probably need some kind of include as well. Let's check that out. So code file send fse.h. No? What's it called then? File send.h. And this is the one we need, I think. Okay, so let's put it right there. Alright, we had it already. And we save, and let's check this out. So echo, and if we turn it on or if we turn it off, and then we have this read key thing, and it calls change echo. So instead it'll call echo and echo. Let's see if this works. So let's see, read key is right. Let's compile. So we run make clean, jump down a little bit, we clear the screen, and we run make. Okay, not too many warnings actually, and only those set but not used. But let's see if this works. So we run fst. Need to give it some bogus arguments. Key. Okay, that's not entirely what I wanted. Why does that happen? Did it update correctly if we do fsd.c bool echo? So what does it do? It creates one of those termios things. It calls on this tcget attribute, cl flag. If we are giving it a true value, probably on, then we will activate the echo flag. Otherwise, we will, let's see, we will AND it with the inverse of echo. So the echo part of it will be zeros. That's right. That should work. But something seems to be a little bit off. I wonder if it's really supposed to be CL flag. I'm not too sure that it should actually, because we have a whole lot of these. So if you do man terminals, let's see if it shows us the structure here. So we have 4 of those, and I always seem to forget which one it is. Perhaps we should just go through them one at a time. So we have IOCL. Let's see. We are using L here. And what did we have? IO. Yeah, I. So let's start with I. I don't think it's I, but let's just go through them all. See if that is the problem. Like so. And we compile, and we run. Nope, that's not it. What else did we have? We have O and then C. So we change this to O, we change this to O, and we change this to O. Save. There is some logic behind this, but I'm not too sure what it is. It can be either way actually, that we are dealing with input or we are dealing with output, because we're dealing with both, and depends on what perspective you are watching this from. Alright, so let's see. What are we going to do? The next thing we're gonna try out is, let's scroll up a little bit. So we had I and we had O, and now it's C. So we do C, and we do C, and we do C. We save. And we run make, and we run this, and I don't really like this actually. Wonder if something else is wrong with this code. But let's try the last one. anyways, and that is L. I don't remember what we had when we started out, actually. We probably tried something twice. Compile, and we run. That looked a little bit weird. Perhaps we should reset the terminal. Right. Okay, so now it works. Did you see that? It asked for the key. When I type something, we don't see anything, but it saves it to the buffer. Okay, that's pretty awesome. So now we are on the track. Let me just check one thing real quick. We don't seem to have a whole lot of activity here. Wonder if I did something wrong. But perhaps not. Never mind. It's probably because of all of those errors. Can't pronounce that word, but all of these bad stream attempts that failed. Okay, so let's keep on at it for a while longer. So let's see. I need to. Okay, the first thing was reading the key, which we have successfully done. We read it to TMP, but we can read it to something more permanent. So let's just call this key, and we will change this to key, and read key is done. Next thing is to initialize the crypto, and if we haven't done that already, we need to add my encryption library to this H file, and it's called arcfour.h in this case. So let's see. The first thing is we need to create an arcfour object. So let's do that, and it's called arcfour like this, and we can name it sorry, we can name it A for arcfour then, or perhaps something better is state, right? So when we have initialized key, we will initialize the crypto, and we do that by calling the function arcfour init, and it takes two arguments. It takes the key and the key length. So we need one more variable, and let's make this an int16, and we call it size. And after we have read this key, we don't need to echo it to the screen, but what we do want to do is calculate its length. So let's just do something like let's do something like size equals we need to cast this to a regular, no, not a regular, we need to cast it to int16. Then we call string length, and inside of it we cast it to a regular char. And then we have the length of the string. Let's also assert that the size is not 0. And now we can just pass the key and the size, like so. And we can assert that we got something back. Okay, so now we can cross this off. That wasn't really time consuming, right? So let's do one more of those today, and then we'll call it a night. And the next thing is we need to decrypt the first 2 bytes of the file. So we need to open the file to begin with, and let's store the FDs here in the file descriptors here in the main. So we will do something like, let's call them in, out. And we're gonna set the in file equal to the what did I make those? Yeah, let's make those in 32 instead, to be to follow the same standard, which means we need to cast this to in 32. Then we call open, and we open our, where do we have it? Our source file. And the source file we will open with the O read only flag. And let's assert that in is greater than 0. Let's also open the out file. So we will do the in32 representation of the open call, and we will the same way open the destination file, but in this case we will open it as write only, and we want to create the file if it doesn't exist and truncate if it does exist. What mode do we want? Let's make this 600. Since we are decrypting a file, there's probably something important with it, right? Something secret. So we don't want to have this readable to the whole world. So let's also assert that out is greater than 0. And now we have our file descriptors. With them and our initialized encryption, what we can do is we can define another int16. Let's call this what should we call this? Let's call it magic. It's not entirely accurate, but it works. So magic will be equal to our own function, which we hasn't defined yet, and let's call it something like grab magic, and we will send our arcfour state. We will send our in file descriptor. At this point we don't need to send our out descriptor. And let's see, we should assert, I think, that magic is greater than 0. I'm not 100% sure though, so let's check the encryptor code and see which possibilities there are. So read key main and pad size is equal to pad size 8 secure rand. Let's see, and where do we have this secure rand? Here. And what kind of data do we get? Seems like we do get 2 explicitly random bytes. So they can be 0, they can be 255, each one of those bytes. Okay, so no assertion. Because we can't really fail with this operation unless the file is, if we can't read the file, if there's some kind of IO error or something. But in that case, we can basically abort from that function instead. So this is what we want to do. We want to grab this magic. And how do we do that? Well, let's see how we deal with that. If we create the function to begin with, it will be an int16. We will call it grab magic, and we send our arcfour state, and we send our int32 file descriptor. And before I forget, let's also update the H file. So let's see, usage string key main. Let's just add it right here. And what did we say? We said in 16 grab magic. And it took 2 arguments, right? One arcfour pointer and one int32. That's right. And this is a pretty basic function. All we need to do is read those 2 bytes and interpret them correctly. So let's create a variable which we call ret, because we're going to return it, and it's an int16. We do also need some kind of buffer, and it doesn't have to be big, so let's just do 8 bytes. It shouldn't be int, by the way. Let's make this int 8. And we will 0 that buffer. And then we will call, let's see, let's create one regular int in this case, which we will call n, just to handle the return value. Because my integers are always unsigned, and we might want to look at the signedness. So we 0 that, and then we will set n equal to read, and we want to read from the file descriptor, but we need to cast it to a regular int, so fd. Then we have the buffer, which we need to cast into a regular char pointer, buff. And then we have the maximum size, which is 7. And just want to read 2 bytes. That's right. So if everything succeeded, then we can assert that n is equal to 2, otherwise we quit. So now we have successfully read this into this char buffer. Now we need to make a 16-bit integer out of it. So let's see how we do this in an easy enough kind of way. Perhaps we need to do, or there are millions of ways we can solve this thing with, but I will choose this method because it's easy on my brain. So I will create another int16, which will be a pointer, and that's right. And then I will simply do p is equal to the int16 representation of the buffer. I think this should be enough. Almost enough. We also need to dereference this, so we do this. Yeah, I think that'll do. And then we'll simply return this ret thing. Okay, it was a rather short episode today, but there will be a whole lot more of these spontaneous live streams. So yeah, that's basically it. If you like this video, please like and subscribe, and thanks for watching. Thanks for today.